Welcome to the solutions to the Regents Physics Current Electricity problem set. Problems numbers 37 through 40. Problem 37. If the circuit in problem 36 has a fuse rated at 12 amps, will the fuse melt if everything is on? Well, as you'll recall from the previous assignment, which we're referencing number 36C, the total current when all the devices are turned on is 15 amps. This, of course, is too much for a 12 amp fuse, and so yes, it would melt the 12 amp fuse. If it was a circuit breaker, it would trip the circuit breaker and turn the circuit off. In this case, it would melt the fuse, which would also turn the circuit off. All right, 38. Determine the reading of each ammeter and each voltmeter shown in the diagram below. All right. First, you need to recognize this is not just a series circuit. This is not just a parallel circuit. You need to recognize that the three 30-ohm resistors are in parallel to each other, and that there's only one path for the current to flow through those and the 10-ohm resistor. So that means the combination of these three 30-ohm resistors in parallel is in series with a 10-ohm resistor. This is called a series parallel combination. Okay, so let's get to solving it here. The first thing that needs to be done here is to determine the total resistance in the circuit. We have to start the problem by determining the total resistance for the entire circuit. To do this, we need to determine the total resistance for the parallel portion of the circuit, and then, since this parallel portion of this is in series with a 10-ohm resistor, add the total resistance for the parallel portion to the 10-ohm resistor to get the overall total resistance. So we start with 1 over Rp, which we'll use for the parallel portion of the circuit. 1 over 30 plus 1 over 30 plus 1 over 30 is 3/30ths, the reciprocal of which gives us the resistance in parallel 30 over 3, which is 10 ohms. We then take that 10 ohms to find the total resistance for all of the circuit, and that total is equal to the total in parallel plus the 10 ohms. So 10 plus 10 is 20 ohms. If you don't understand any part of how the total resistance was determined, make sure you ask in class tomorrow. Now, since we know the total voltage and the total resistance, we can find the total current measured by ammeter A. And that's the reason we found the total resistance first, is because you recognize that ammeter A1 measures all of the current. So we go ahead and apply Ohm's law here. I equals V over R. Total voltage of 45 volts. Total resistance of 20 ohms. So the total current is 2.25 amperes. Now, knowing this current flows through the 10 ohm resistor, we can figure out the reading of voltmeter V1. We know that this 10 ohm resistor gets all the current. We know that it's 10 ohms. So we can apply Ohm's law, V equals I times R, 2.25 times 10 ohms of resistance equals 22.5 volts. Now, knowing the voltage through that resistor, we can figure out the voltage left for the parallel portion of the circuit by subtracting from the total voltage. Since the three 30-ohm resistors in parallel, they all get the same voltage, so the reading in voltmeter V2 is equal to the reading in voltmeter V3. So V2 equals V3, which is going to be the total voltage, 45, minus the amount used up by the 10 ohm resistor on the top there, 22.5, which is also 22.5 volts. Now, knowing the voltage that the 30 ohm resistor gets, we can figure out the current I2. Apply Ohm's law, I equals V over R, 22.5 volts over 30 ohms equals 0.75 amps. These types of problems are very similar to Sudoku puzzles. If you like to do those, you find one answer that leads you to the next answer, which leads you to the next answer, okay, and that leads you, of course, to your last answer. And it all fits together and checks when you're done. Number 39 wants us to determine the power used by each resistor in the diagram shown above. So in the previous problem, the power in the 10 ohm resistor P equals V times I. You can actually use any of the power equations, but this is the easiest one. You know the 10 ohm resistor uses 22.5 volts, and it gets the total current of 2.25 amps. This gives you 50.6 watts of power. The power in each of the 30 ohm resistors, each gets 22.5 volts. Each will get a third of the current that flows through that, and a third of 2.25 is 0.75 amps. So 22.5 times 0.75 is 16.9 watts. Lastly, we have number 40 here. A typical home circuit is diagrammed below. Note that the lead lines to the kitchen lamp each has very low resistance of 0.25 ohms. I'm telling you these wires have resistance 0.25 ohms. The lamp has a resistance of 240 ohms. And although the circuit is a parallel circuit, the lead lines are in series with each of the components in the circuit. You can see the power saw is in parallel to the kitchen light. All right, compute the equivalent resistance of the circuit containing just the light and the two lead lines. Well, just the light, if the power saw was turned off, and the two lead lines are in series. So we simply add them together, and we get the total resistance 240 plus 0.25 plus 0.25 to be 240.5 ohms. Find the current to the bulb. I equals V over R. You found the total resistance and the total voltage. Since it's in series, that total current remains constant. 120 over 240.5 is 0.499 amps. Find the power dissipated in the bulb. You can use any of the power equations, but the easiest one in this particular case is P equals I squared R, because you already know the current. So go ahead, 0.499 squared times 240, 59.8 watts. For part D, because the current in the bulb is 0.50 amps, the current in the lead lines must also be 0.50 amps. Calculate the voltage drop across the two leads. Well, the voltage is simply how much of the voltage each of these resistances uses up. So 0.499 amps times 0.25 ohms. They each use up 0.125 volts. All right, that'll do it on our solutions to problems 37 through 40. More to come as we wrap up the problem set and finish current electricity by doing problem 41 together in class tomorrow.